Welcome to Module 7a, focusing on subsurface geomechanics, sequestration thermodynamics, and seal integrity. This video provides a detailed examination of the complex physical interactions within these subsurface systems. It's prepared by Dr. Fahed Qureshi from National University of Singapore. This module explores the intersection of geology, thermodynamics, and mechanical computation. We will cover poroelasticity thermodynamic principles, seal integrity, and coupled THMC and AI methodologies. In Section 1, we examine advanced poroelasticity, specifically focusing on subsurface stress tensors, transient volumetric strain, and dynamic elastic moduli shifts resulting from CO2 injection cycles. Understanding stress partitioning is essential. We differentiate between the total stress tensor, which accounts for overburden and tectonic loads, and Terzaghis effective stress, which directly influences rock framework behavior and microfracturing. The Biot-Willis formulation helps quantify how pore fluids counteract external loads. Key physical drivers, such as rock mineralogy, burial depth, and diagenetic compaction, significantly influence the poroelastic coupling coefficient. Injection pressure can induce dynamic shifts in elastic moduli. As pore pressure increases, we observe changes in stiffness and shear load capacities, including reductions in Young's modulus and the decay of shear modulus. Pore pressure transient diffusion illustrates how pressure gradients evolve over distance. These localized volumetric strain gradients are most significant near the completion casing boundary. 3D spatial stress path mapping allows us to visualize how reservoir pressure affects surrounding formations. We track horizontal stress parameters and swelling strain to identify high-rate risk zones prone to mechanical failure. Section 2 moves into sequestration thermodynamics and interfaces. We will discuss advanced equations of state, density and harmonicity, capillary hysteresis, and pressure envelopes. Standard cubic equations like Peng-Robinson often struggle near supercritical boundaries. In contrast, the Span-Wagner formulation, based on Helmholtz energy, provides superior precision for density calculations in these complex environments. The Span-Wagner equation maps critical density shifts across various phases, including the stable dense phase, the near-critical instability boundary, and the subcritical two-phase envelope. Trace impurities significantly impact phase envelopes. Components like nitrogen, methane, and sulfur oxides modify critical temperature and pressure, ultimately affecting the geomechanical integrity of storage seals. Corey and Brooks-Corey models regulate relative permeability in CO2 systems. Interfacial tension gradients dictate fluid distribution and control the behavior of capillary heterogeneity trapping. Interfacial tension is dynamic, influenced by salinity and thermal gradients. Additionally, capillary hysteresis, characterized by a mismatch between drainage and imbibition, can trap CO2 as isolated microbubbles. Finally, we consider how wetting angles change with mineralogy. Quartz, feldspar, and clay minerals exhibit different wetting characteristics, which directly impacts the efficiency of capillary trapping for long-term sequestration. This module explores caprock micromechanics. We will examine the physics of capillary sealing, Young-Laplace formulations, micropore modeling, and the processes behind chemical mineral degradation. Capillary sealing is governed by the Young-Laplace formulation, which defines the entry pressure limits for caprock matrices. We must account for pore throat constraints, mineral distributions like illite and chlorite, and the risks of dynamic seal degradation. Maximum buoyant CO2 column limits are determined by buoyancy stress constraints. A caprock sealing capacity depends on density differences between reservoir brine and supercritical CO2, with exceeding these thresholds risking fluid migration. Carbonic acid degradation is a critical long-term concern. Processes like pore water acidification, carbonate dissolution, and aluminosilicate weathering can alter seal integrity, while diffusive leaching loss occurs over millennial timescales. Acidic brines cause microfracture dissolution, selectively weathering calcite on fracture walls. This creates bypass channels that increase caprock permeability by orders of magnitude over decades. Clay mineral matrix diffusion involves the gradual conversion of swelling smectite and illite into stable kaolinite. This structural transformation changes matrix volume and alters capillary entry pressure limits. We now transition to coupled THMC modeling, covering non-isothermal injection effects, thermoporoelastic coupling, and geochemical scaling hazards near the wellbore. Non-isothermal injection creates localized thermal shocks. Cold CO2 injection into hot reservoirs induces matrix contraction, which reduces confining stress and potentially generates new thermal fractures. Near wellbore salt scaling is driven by vaporization. As dry CO2 evaporates pore water, halite precipitates and restricts flow. Mitigation strategies include freshwater flushes and water alternating gas schedules. The next section focuses on fault reactivation risks, specifically analyzing Moore-Coulomb failure envelopes, induced seismicity, and the application of traffic light control systems. The Moore-Coulomb shear formulation quantifies failure on pre-existing fault planes. Elevated pore pressure reduces effective normal stress, pushing the stress state toward the failure envelope and increasing slip risk. Traffic light systems manage seismicity. Operations proceed at green, require caution at amber by reducing injection, and mandate immediate shut-in at red if magnitude thresholds are exceeded. Wellbore integrity is vital for long-term storage. We must address mechanical debonding of the microannulus and the degradation of standard Portland cement when exposed to acidic sequestration environments. Portland cement is susceptible to carbonation, turning soluble under acid exposure. To improve durability, engineers utilize acid-resistant alternatives like epoxy resins, geopolymers, or calcium aluminate. Finally, we explore the use of AI and surrogate models, including physics-informed neural networks and satellite-based INSAR data for geodetic monitoring and subsurface back calculations. Physics-informed neural networks incorporate governing physical laws directly into their loss functions, ensuring predictions are spatially mass-conservative. Meanwhile, Fourier neural operators bypass standard grid restrictions, enabling ultra-fast execution and real-time monitoring of pressure gradients and CO2 plume migration. Beyond modeling, deep learning enhances monitoring. Distributed acoustic sensing uses convolutional networks to filter noise and detect seismic events, while INSAR satellite data enables autoencoders to interpret surface displacement and reverse engineer subsurface stress vectors. This concludes our module on advanced subsurface geomechanics and thermodynamics. Dr. M. Fahad Kureichi is available for consulting, research collaboration, and technical training. Please feel free to reach out via the contact channels provided.